All right, who'd like to start us off with a prayer? Anyone?
I'm standing.
Thank you.
Our dear Father, we thank you for this day. We're able to come here and be able to have this wonderful snow starting to fall down this week. Please bless that they have safety in our journeys and that the last time we had this week, they will be able to prepare ourselves for the finals and our upcoming tests in all our classes. Please bless for the glory that he may feel better, that he may enjoy his things to be great and not be sick the whole time. And please bless us to enjoy this time with our families and not take it for granted. In the name of Jesus Christ, amen.
Amen. Thank you very much. Yeah, I have a cold. The cold hasn't been that bad. It's the headache that's come with it that's been the bear today. Thanks for the prayer. So while you're working on this iClicker quiz, just a reminder, we have an exam coming up. I think it starts the Wednesday after we get back. It's 25-ish problems, all multiple choice, in the testing center. There's review materials already up online. Same place where the other review materials have been on Learning Suite. You can still work on the exams from the math lab has some exams on there. Brindley was telling me that some of the keys, though, there's a few problems where the keys are incorrect on those. But then I have a couple other old exams or review sheets there with answers on them. So study hard. You will find some problems on there that is on material that's either already been tested or things that we haven't got to yet. So if you find anything about parametrics or polar equations, then you can just skip it. You'll recognize that we haven't covered it. But the exam is only 11.3 through 11.11. So we tested up to 11.2 on the last exam. So those are what you want to study hard. Any questions before we begin? Okay. I'm going to write down a few other problems for you to start working on after you finish the iClicker. Okay.
not sure which option is best. Essentially, just take out the power and just spend it. Because it's the same thing as we're in the whole thing. Although we're just running no. Yeah. So,
there's 2 or 3 ways to make it come. One way that really here's some we have to write out the turn on. We have to distribute that one to the series and that X to the whole series and the X to the whole series. It's actually not hard to have it, but do it pattern shows. There's another way, 1 over 1 minus 6, where X is 1 over 1 minus
There's a little hint on number 1. Okay, so let me turn on my mic. This section, 11.9, is to practice taking a known power series and adapting it, using substitution, using some multiplication, using antiderivatives, using derivatives to get new power series that keeps you from having to take a whole bunch of derivatives and trying to find patterns in those derivatives and using the Taylor polynomial, using the Taylor series formula. So in this section, they actually only have you work with one power series, and that is this power series right here. Okay, this geometric series. So you're used to seeing this with maybe 1 over 1 minus r, where r is a common ratio, or a1 over 1 minus r. And this is true as long as x is in absolute value is less than 1. So remember, this was the formula that the philosophy professor made a mistake using by plugging x equals 2 into both sides. Well, it's not true if you plug in x equals 2. So you have to use values that are within the radius of convergence. So so how do we do this with this first problem? Well, I'm going to factor out a 5 in the denominator. What I need to get this number to be 1, because I can use this function here, this power series, if I can write it as 1 over 1 minus something. I need to get it in that form, 1 over 1 minus something. So if I pull out a 5, then I can get that 1 over 1 minus something. I pull out that 1/5 here, and then it's a substitution problem. I just take that x to the 5th and plugged it in wherever there was an x in my formula. So instead of x to the n here, I have x over 5 to the n, which simplifies to x to the n over 5 to the n. And we could go one step further and take that 1/5 outside, put it in, so that raises the power by 1. So you don't have to have written it that way for the iClicker quiz. So any questions on this? Yes? Yes. Yep. Yeah, as long as whatever you wrote could be simplified into that equivalent, you're good. Yes? Yep, either one should be fine. So. The hard part with the multiple choice problem is we get to write it and you have to recognize it, and so sometimes there's a little bit more work because you do the problem and you see it there, but we may have written it in a different form. It's one of the disadvantages of a multiple choice question. So we try not to make them too crazy. All right. So I'm going to turn you loose again to work on 1, 2, and 3. I'm just highlighting that there are different ways to do this problem. We will do this one in a couple of ways, but the easiest way is to recognize that if you take 1 over 1 minus x and take the derivative, you get 1 over 1 minus x quantity squared. So how can you use that and the power series for 1 over 1 minus x to get the power series for 1 over 1 minus x squared? So take a few more minutes, work on wherever you were at, work on these. There's a hint for number 2. There are different ways to do these problems. Okay, so there's lots of different ways to do these problems. But there's one way you can go for number 2. Pay no attention to the man behind the curtain. All right, let's start working through some of these. So, like I mentioned before, there are different ways to approach these. Some are easier than others. So, a lot of you recognize that if you squared this power series, you'd get what we wanted to find. A lot of you wrote this. Supposed to be an infinity. Oops. But that is not correct. Okay. Why not? Well, let's look and see what this is correct. Okay, up to here, we're good. But what happens if you want to multiply these things? Well, one of these things is 1 plus x plus x squared plus x cubed plus x to the fourth, right? Squared. So that's 1 plus x squared plus x cubed dot 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 times 1 plus x squared plus x cubed dot dot dot. And you can multiply these, you just have to go term by term. 1 times 1 is 1. 1 times x is x. 1 times x squared is x squared. 1 times x cubed is x cubed. And then x times 1 is x. X times x is x squared. X times x squared is x cubed. So what you do if you're doing this, you hope you can find a pattern so you don't have to do this for the rest of your life, right? So, and a nice pattern emerges here. So multiplying x squared by 1 is x squared, and then x squared times x is x cubed, x to the fourth, etc. And you start adding these up. What do you get? You get 1 plus 2x plus 3x squared. We haven't finished going further, but you get x cubed plus x to the fourth and then plus x to the fourth dot dot dot. So 4x cubed plus 5x to the fourth, etc. So you can do it this way. You can multiply power series. You just have to go term by term, combine the like terms. Okay? It's not the ideal, as you can see. Okay? And this is about as simple as you can get to do this. So this is one strategy. If you want to figure out what the power series is for something like e to the x times sine of x, then you could start taking derivatives of this thing. And you've got to do product rule, and then you get, it's kind of crazy to take all the derivatives. It's probably easier to just start multiplying their power series. So you have 1 plus x squared over 2 plus x cubed over 3 factorial dot 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 times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, dot, dot, dot. And then you can just start multiplying and combining like terms. So it's another strategy. Okay, the slicker way to do this, a slicker way, is to recognize that the derivative of 1 over 1 minus x is 1 over 1 minus x quantity squared. So they're not only connected by a squaring feature, they're connected by a derivative. So one of the things it talks about in this section is that if you know the derivative of, if you know the power series for one function, when you take the derivative of it, you get the power series of that derivative. You take the derivative of both sides, those derivatives will still be equal. And the radius of convergence will be equal. So let's work on this way. So 1 over 1 minus x is 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th, dot, 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 x to the n. And let's just take the derivative of everything. So over here you get 1 over 1 minus x quantity squared. Here, let me do it this way. So this is really 1 minus x to the minus 1, right? So you do the power rule to get minus 1. 1 minus x to the minus 2, but then you've got to do chain rule to get minus 1. And that whole thing, these minus 1s cancel out and or multiply to a positive 1, and you get 1 minus x to the minus 2, which is 1 over 1 minus x quantity squared, which is what we're trying to find. Well, that's the derivative of the left side. Well, what if you start taking derivative term by term over here? You get 0 plus 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th, dot, dot, dot. And isn't that exactly what we had up here? Yeah. So works this way too. And you can even jump right to the general form. So the derivative of that is let me not put that on there yet. So n x to the n minus 1. Now the big question though is, where do we start? Because we had, at n equals 1, we had this 0, we had this constant term, but that went to 0. So now I don't have to start at 0, I start at n equals 1. It actually does, it doesn't hurt us. We can still start at n equals 0 in this particular case, because you get a 0 times an x to the minus 1. But that's not always the case. You have to check and make sure you change your indices if you need. So. Okay. Any questions about this problem? Well, if you lose the first term, so this is one reason I was really comfortable if I wrote out the first several terms like I was doing right here, and then going to this, because then it made it really easy for me to know where the index should be, because I could think, well, my first term's really 1, so what do I need to, what n do I plug in here to get out 1? And if you plug in n equals 1, you get out 1. So I'm like, oh, great. I can just start at n equals 1. So it helped me if I actually wrote these first few terms out when I was finding derivatives or antiderivatives and stuff like that. I could more easily reason through what that index would be. So you don't always lose a term when you take the derivative. For example, if you have sine of x, you have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Right? If you take the derivative of this, you don't lose a term. Your x goes to 1. So there, your index might not change at all. You'd still, if you were starting at n equals 1 here, you could still start at n equals 1 there. So, but if you take it again, that term's going to go to 0, and you've got to probably shift your index. Great. Other questions? So I'm going to write down something. So I'm going to take this, just write it down here. Just making sure I have enough room here. I'm going to write down a series you've actually seen before. So look at the one on the right and try to remember, where have you seen that series before? Raise your hand if you know where you've seen that series before. Christian? The dice game, the game of pig that you guys did in lab. We generated a series that the sum of that series was the average number of times you need to roll to get a 6. Well, so that's what this represents, the average number of times to get a 6. And up to that point, we did not have ways to find sums of things like that. But now we do. If we recognize that this is a series, this is a power series where x is just set equal to 5/6, then we can go back and find the sum. So this piece is 1 over 1 minus x quantity squared. So that means this piece is 1/6 of 1/6 times 1 over 1 minus 5/6 quantity squared. Oops. So the denominator, 1 minus 5/6, gives you 1/6. You square that, you end up with 1/6 divided by 1/6 squared, which is 1 over 1/6, which is 6. So the sum of that crazy infinite series that we got when you were doing the dice game, the actual value was 6. Some of you I know had other ways to reason through why it should be 6. So, but at that point, the best we could do was integral estimation, or put it into Excel, try to add up a whole bunch of terms. Hope we could see something, that might approach a number. Okay. So one of the points of this is we now have 3 ways to figure out the sum of a series. We ran into 2 very early. So if it's a geometric series, a convergent geometric series, we have first term over 1 minus the common ratio. What's another way we know? So we learned in 11.2. What's another kind of series that we can find the exact sum? Telescoping. And we've just learned a third. So a special instance of a known power series. So, for example, if I write down talk to your neighbor, what does that series equal? All right. What does this series look like? It looks a lot like the E power series, except what? There's 2's instead of x's. E to the x is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial. Right? But it looks like everywhere there's an x, there's a 2. So then just plug in a 2 on this side. So e squared would be the answer. That series converges to e squared. So, all right. So this is another one where there's lots of different ways. I put this on here to talk about one particular technique. Okay, so you can break this up and find the power series of each one. And then you can start adding and combining like terms. So that's what I'd like to see each of you guys work on right now. So find the power series for each of these. We already found that the power series for 1 over 1 minus x quantity squared is nx to the n minus 1. So how do you use that to find each of these? And then add those together. See what power series you get. Okay, so this is one way to do this problem. Is you can split it up as a sum. So that's what I did here. I put it into two different pieces, and then I found the power series for each of those by rewriting the first one as x squared times 1 over 1 minus x squared, and the second one as x times 1 over 1 minus x quantity squared. I had previously found the power series for 1 over 1 minus x quantity squared. It's right here. So I distributed out the x squared to that series, distributed out the x to that series, and then I just added up those two terms, those two series, term by term. And then you hope that you can find a pattern. Okay? So this was nice. The coefficients were 1, 3, 5, 7, 9. So that makes it a nice 2n minus 1. And the powers of x were just went up by 1, starting at 1, 1, 2, 3, 4, 5. So I made n equals 1 as my index. That's where I started. And we're good to go. Questions on what I did here? There are other ways, and I'll show you one other way. But any other questions on this? Okay. So another way to think about this problem is you could rewrite it as, let's go back to the original, x squared plus x over 1 minus x quantity squared. You could think of this as x squared plus x all times 1 over 1 minus x quantity squared, which is x squared plus x multiplied by this power series. And then you can multiply each of these out. You can distribute those out to that series and then combine like terms. So x squared plus x times 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the fourth, etc. So x squared plus 2x cubed, etc. And you can see that this is similar to what we did before. We're going to get the same terms. And then when you multiply out your x's, you get an x plus a 2x squared plus a 3x cubed. Sorry, I'm writing small here. Plus a 4x to the fourth. And you keep on going and you add those up and you'll get the same thing. So you get the x plus 3x squared plus 5x cubed plus 7x to the fourth, etc. Okay? Questions on this? All right, have a great day. See you tomorrow. It's Friday tomorrow.
Question. There's supposed to be a written homework due tomorrow. Is that true?
No.
Okay, it's on the
due.
calendar, but okay.
Yeah, one of the TAs sent out an email about that.
Did she?
So,
Okay, I guess I haven't
thought
seen
you
it
did.
yet.
So,
Okay.
yeah.
That's fine. Thank
Okay.
you.